All right, let's just dive right into this explainer and look past the buzzwords of renewable energy to uncover the actual physics and engineering behind solar power. We hear about solar panels all the time, right? But the mechanics of how we literally capture a star's energy and plug it into our daily lives is a truly fascinating story, one that bridges ancient astronomy with cutting-edge global economics.
To really get a grip on this, we're going to hit 5 key areas today: the renewable energy boom, the summer heat paradox, engineering the perfect angle, global mega solar parks, and finally, off-grid versus connected systems.
Okay, let's kick things off with Section 1, the renewable energy boom. We're talking global economics here.
So the really crucial point here is that back in 2015, manufacturing advancements drove solar prices down to an incredibly low 4 cents per kilowatt hour. We saw this in massive projects like Aqua Power's solar plant in Dubai. And actually, right around the exact same time, wind farms in Egypt were hitting that exact same low price point. Now, you might be wondering, why does 4 cents matter so much to your wallet, let alone the global economy? Well, historically, fossil fuels completely dominated because they were cheap and reliable. But 4 cents a kilowatt hour, that completely disrupted the whole game. It was literally the tipping point that took solar from being this, expensive niche green alternative to a strictly logical economic choice for major cities. The sudden drop in cost made local emission-free generation a massive economic advantage. It reduced our total reliance on sprawling, expensive traditional grids and, most importantly, directly lowered the cost of keeping your lights on.
And this brilliantly illustrates the massive scale we're actually talking about here. If we look at 2013 data, China led the global charge with 378 gigawatts of renewable energy production. The United States followed at 172 gigawatts and Germany at 84. Now, to really put that into perspective for a second, just one single gigawatt is roughly the total energy output of a massive nuclear power plant. So when we talk about China producing 378 gigawatts, we are literally talking about the equivalent of hundreds of nuclear reactors worth of energy just being harvested directly from the environment. It shows this incredibly powerful global shift toward new energy that honestly has only rapidly accelerated in the years since. Moving right along to Section 2, the summer heat paradox. Let's get into some planetary physics.
I want to ask you a deceptively simple question. Why exactly is summer hotter in degree than winter? Take a second and just think about what you were probably taught growing up.
Most people intuitively think, well, we must be physically closer to the sun in the summer. I mean, it totally makes sense, right? You get closer to a fire, it gets hotter. But the reality is the exact opposite. We are actually further away. Our physical distance from the sun isn't what cranks up the heat during those dog days of July and August. It's actually all about our planetary posture. Now, I know it feels incredibly counterintuitive at first, but once you understand how our planet physically sits in space, the whole mechanics of solar power make absolute sense. Notice the Earth's elliptical, or, oval-shaped orbit in its permanent 23-degree tilt. Because of that oval shape, during the northern hemisphere summer, we are actually on the wider part of the orbit. We're physically further away from our giant nuclear fusion reactor of a sun. But because our planetary posture is permanently tilted at 23 degrees, during those summer months, the northern hemisphere leans directly toward the sun. That means the sunlight hits us far more directly, travels through less atmosphere, and basically bathes us in light for much longer periods during the day.
Think of it like a simple flashlight. If you shine it straight down on a piece of paper, the light is highly direct, it's concentrated, and it's intense. But if you tilt that paper, that exact same amount of light spreads out, diffuses, and cools down. Our 23-degree planetary tilt gives us that direct, highly concentrated flashlight beam in the summer, and that exact concentration brings maximum heat and maximum light, which, as it turns out, is precisely the raw energy that solar panels are constantly hunting for.
All right, that brings us to Section 3, engineering the perfect angle. This is where the math comes in. So, because of how the Earth rotates relative to the sun, the absolute golden rule for anyone in the northern hemisphere is that panels must always face south. Whether it's the dead of winter or the peak of summer, the sun's path will always have a southern inclination from our perspective of north. And hey, just to keep us globally aware here, the exact opposite is true if you live in the southern hemisphere. Down there, your solar panels must always face north to catch those prime rays.
But how far should they actually tilt to face south? Well, to capture the absolute maximum of the 1,000 to 1,300 watts of solar energy hitting every single square meter, engineers use this brilliant little formula based precisely on your geographical latitude. During the spring and fall, the perfect tilt is exactly your latitude degree. But in summer, you subtract 15 degrees, and in winter, you add 15 degrees. The real-world stakes of getting this math right are massive. If a solar farm doesn't adjust for that plus or minus 15 degrees, they miss out on capturing those crucial 1,000 to 1,300 watts. On an industrial scale, that tiny mathematical error is literally the difference between a highly profitable solar farm and a catastrophic financial loss.
Notice how the sun's trajectory across the sky physically changes with the seasons. You have to adjust the angle by 15 degrees because the sun is literally taking a different path above your house. In the summer, the sun arcs incredibly high overhead, so panels need to be laid flatter to face it directly. But in the winter, the sun stays much lower on the horizon, practically peeking through the trees. So the panels need to stand up much steeper to catch those direct, concentrated rays.
Because your optimal angle is intrinsically tied to your specific latitude, the engineering required to set up a solar farm in London is mathematically very different than the engineering required in Cairo or Riyadh or Tokyo. The fundamental physics of the sun's radiation, they remain exactly the same no matter where you are, but the practical geometry changes entirely depending on where you are standing on the globe. It's a truly stunning global scale of engineering, where every single localized project requires bespoke mathematical calibration to effectively harness the stars.
Let's zoom out a bit for Section 4, Global Mega Solar Parks. We're talking massive scale now. When we build at this global scale, and we apply all that localized math we just talked about, the numbers become absolutely staggering. We're talking about colossal installations, like the 400 megawatt Agua Caliente project in Arizona, 300 megawatts at the Charanka solar park in India, and 200 megawatts at the Golmud solar park in China. These aren't just your standard neighborhood rooftop setups, right? These are vast industrial powerhouses. They effectively act as massive energy sponges, deliberately laid out across some of the most sun-drenched deserts on the planet, soaking up radiation on an unprecedented scale. To truly put that scale into perspective, the Agua Caliente project in Arizona cost hundreds of millions of dollars to build, and it utilizes 5 million individual thin film panels spread over nearly 10 square kilometers. Just imagine that for a second. An absolute ocean of perfectly angled glass, nearly 10 million square meters large, sitting out in the blistering heat. The sheer logistical feat of building something this massive is mind-boggling, let alone maintaining it. I mean, you have to keep 5 million fragile panels perfectly clean and functioning in a dusty, harsh desert environment just so they can silently harvest radiation from a star millions of miles away. It's incredible.
And finally, Section 5, Off-Grid versus Connected Systems. Let's bring it back home.
For our final section, we really need to understand how all of this immense generated power actually reaches your home. It's one thing to harvest electricity in a desert, but it's another entirely to make it usable for your television and your refrigerator. If you've ever considered putting panels on your own roof, this is the ultimate decision you have to make. You basically have two options. You can stay off the grid entirely with a standalone system, using large battery banks to store that daytime sun to use at night. Or you choose a grid-connected system, linking directly to the broader utility network. Standalone gives you total independence from power outages, but a grid-connected system? That allows you to feed your excess power back to your city, effectively turning your own house from a mere consumer into a miniature active power plant for your local community.
And to squeeze out every final drop of efficiency, whether we're talking about a megapark or a high-end local setup, many of these systems utilize what's called sun tracer technology. Instead of locking panels into one static angle based on that seasonal math we talked about earlier, these trackers physically move. Imagine these massive panels slowly turning their faces like giant sunflowers, tracing the sun from the exact moment it peaks over the eastern horizon until it sets in the west. This ensures that the intense, direct flashlight beam we talked about is captured perfectly, at the absolute most optimal angle, from dawn until dusk.
Which leaves us with a truly fascinating thought. As local generation becomes perfectly engineered and the cost of parts continues to plummet, how will the traditional power grid survive this solar revolution? When massive desert parks and local neighborhood rooftops are all dynamically tracking the sun and feeding energy locally, the entire centralized way we've historically managed global power is going to have to completely evolve. From the 23-degree tilt of our planet to millions of dynamically tracking panels, the future of energy is already here. I hope this gave you a solid understanding of the incredible mechanics behind solar power. Keep exploring the science around you, and thanks for joining me on this explainer.